So, I'll talk about programming languages. And so we will have two theoretical lectures on the topic and in the section. So maybe this is the most important slide. So I don't know much about biology, to be honest. Okay, so since I graduated from high school, I've never been formally introduce any more biology topics. Anyway, so in fact, biology was my least favorite topic in high school. But I like doing optimization. So I'm an industrial engineer. So I obtained my PhD degree in operations research. So I do a lot of optimization, all different kinds of optimization. I'll talk about it briefly later on. So that's why, since I don't know biology, which I can explain the problem today, I can explain through math and optimization, operations research techniques. Right, so I think the math presentations will be if you know a little bit of optimization. Okay, except for a few slides that I will cover. So this is really deep optimization. You don't need to understand it for now. But for most of the slides, I hope that at least the ideas will be sort of clear and understood. Okay, so here is the outline for the first part. So since I expect the audience not to be fully familiar with what operations research means or optimization means, I have about 10 to 15 slides explaining what operations research is and why we use it and the relevance of the time machine. Okay, then I'll have a quick introduction to biological time machines, again, the way I understand it more mathematically. Then I'll talk about what I would like to call it the static deterministic model. So you will see why I call it like this when we get there, and then I'll show you a little bit of commutations. Okay, so a gentle introduction to operations research. I will talk about optimization and a little bit of processes, and in particular something called operations. Okay, so here is an example to just motivate you for optimization. Suppose that you would like to pack your knapsack for a vacation. I think knapsack is a really old word to say backpack, essentially. I think only the operations researchers now use this really word. But you know, your knapsack, your bag is a finite capacity, so you cannot really put everything that you have in your knapsack for the vacation. But let's keep it simple and suppose that you have 4 items to choose from to put it in your knapsack. And we have these values, how important that item is. Okay, so I give this for 4 items, 5, 7, 4, 3, the numbers don't match. And then you have the size of these items. And the knapsack has a capacity of 40. So as you can see, we cannot put everything in your knapsack, so it will exceed the capacity. Now you have to choose some items from this list so that the value in your knapsack is as big as possible. Right? So that's a simple looking problem from optimization, and we use this in different contexts. Okay, so here's a question to you. Can you give me an upper bound on the number of ways you can organize your knapsack? Okay. So here's an organization. I put nothing in my knapsack. Okay, so that's a trivial organization. Certainly it doesn't maximize anything, but it is one possibility, right? Can you answer this question? How many ways you can organize knapsack?
I mean, with the constraint of the size or just in...
Yeah, so that's why I said overall. So let's forget about the constraint. To make it really trivial question. Well, you have 4 items, and the way you can organize it is the number of subsets of these 4 items, which is 2 to the power 4. So you have an upper bound of 16 different ways to organize your knapsack. Of course, not all of them are easy, meaning that For instance, I cannot put all of them in the stack. So that should be somehow taken out of the feasible, possible organizations. Okay, because this is a simple problem, I think we can solve. What are the best items to select?
Yani civil ports being valued.
Yes, if I choose 7 and 4, it won't fit.
Oh, then
capacity is, yeah.
Capacity is but I was
8 and 6.
Yeah, if the capacity, if you use the item value 5 and the item value 4, the total is 9, and they just barely fit the knapsack. And if you look very carefully, that's the best you can achieve. Very good. And now the sort of open-ended and ambiguous question. Do you think this is an easy problem to solve or a hard problem? Whatever it is. So there's a formal way to define zero optimization problems. But what do you think? It seems really easy to state the problem, right? With knapsack items. Any ideas?
It's exponential.
Yeah, I already gave a hint, sort of a hint. Since the way you can organize the number of items is exponential in the number of items you have, 2 to the power n, let's say, if you have items. So it seems like you have to check a lot of text to find the optimal solution. Well, that's not exactly true. In optimization, we almost never check all of possibilities. We have some clever ways of doing it. But in the worst case, we may have to. Okay? And this is a problem in which you may have to do it. Okay. Right. And here is a more mathematical description of the problem. So suppose that I have the set I, which represents the set of items, and I have a value for each item, size for each item, and the capacity of each. So this is what we call as parameters. The parameter means that they are given to me. I'm not allowed to change it. Okay. Let me give you another example. Let's say I'm producing chairs. I have a facility, and I have 10 machines to produce. So that number 10, the number of machines I have, is a parameter. I cannot simply think that, well, even if I have 10 machines, let's plan as if I have 15 machines. I cannot do it, right? So that's the number given to you that you cannot really change. And so that's the definition of parameters. So I know that in some other engineering discipline, they talk about parameters. So that's very counterintuitive to an operations researcher, because for us, parameter is fixed. You cannot change. What you can change is called a decision. Okay? Because these are variables that can really change, and we decide on them. Okay?
So when you call them hyperparameters, in machine learning, you call them hyperparameters because
yes.
the parameters.
Yeah. Exactly. So there's even in machine learning, or pretty much in other heuristic algorithms as well. So there are some parameters you fix. And then you run the algorithm, you change the parameters, you run the algorithm again, you get different results. Perhaps it's faster or slower, more accurate, whatever. And then they talk about hyperparameter, in which they try to find the best parameters for the algorithm to work the way you want it. Okay, so here's the decision variables. In this case, we define a decision variable xi, taking value 1 if you actually select that and 0. So such variables are called binary variables. Very intuitive. Right. And using binary variables, I can formulate an optimization. And here is how I do it. So by the way, optimization problems have several components. The first one, the way it's written here, is called the objective function. So that's the function you want to maximize or minimize. In this case, we are trying to maximize the value, so that's why I'm maximizing this function. And function looks sort of simple. So you multiply the value of the item It's the variable xi. What does that mean? So if xi is 1, if I really choose that item, that I count vi, it's vi. Otherwise, if xi is 0, if I don't put that item in my left stack, then vi times 0 is 0, so that's it, whose value is not counted in my range. Yeah, so that's how we do it for the function. And then, so this concept is very important, constraints. Okay, so it essentially means that these are the rules you have to obey. So you cannot pretend that your knapsack is more than 14 units in size. Okay? So you have to respect it. And how do we respect in this case? Well, very similar. If you put the item, then you count the size. If not, you don't count it. And the left-hand side of this equality gives you the size of the items that you select. And it should be at most C, cannot exceed C capacity. Right. And finally, some problems you have to specify the domain of the decision variable. In this case, the variables are binary, so I'm calling them as 0. Okay. So the values should come from this 0. Okay, so the nice thing is that I will talk about this later on again. So this kind of problems, again, I'm not specifying the kind of problem for now. It means really efficient general purpose solvers. So it's not theoretically true that we can solve any knapsack problem very efficiently, but in practice, we have really good solvers now, which hopefully we will use in the afternoon. That they're able to solve problems which look like this. Any questions? By the way, please do interrupt me if you have any questions. We have to talk more about optimization always. So here are more examples of optimization problems. So I deliberately choose some combinatorial kind of problems which are easy to explain. So this is not how we start teaching optimization in undergrad. So we start with something called linear programming. But I think this is easier to understand. So let's look at this graph. You can even think of this as a network if I put arrows for the edges of the network. Again, for those of you who may not be familiar with the terminology, so these circles are called nodes or vertices of my network or graph. And these line segments are the edges or arcs if I put arrows. So sometimes people call it link or connection. And things like that. Then once we have a graph, you can ask really interesting questions and formulate them as optimization. For example, short step. So today you were at your home or your dorm, let's say point 1, and 6 is this campus. So there is no direct link from 1 to 6 as you can see. So you have to go through it. So what is the shortest way you can actually achieve? Okay. So obviously it depends on where you start and where you want to go. And so these are called source and sink. And the network itself. So for example, for me, I live in Swabia, I took maybe the Marmaray and then N5 and reached here. So that's one. Okay, so it turns out that the short spread problem is actually an easy problem. And more formally, it's something called solvable. I will not explain what that means precisely, but think of it like, okay, this I can solve. Right? But one thing you should observe here is that there are really many ways to go from 1 to 6. Okay? But the nice thing about this problem is that you don't need to look at all of them. Okay? So there's a smart way of doing it, so which runs in polynomial time, although there are potentially exponentially many ways you can do it. Okay? And there are many algorithms to do this. One popular one is Dijkstra's algorithm, there's Davenport algorithm. Okay. Now let me show you another problem, which is defined on the same network. Okay. And it's called the traveling salesperson. Again, these operations research people are very new. They use this interesting terminology. So suppose that
Used to be called traveling salesman problem. So now they're gender equal. So you do progress.
yeah, that's good. So for TSP, the sales field is as follows. Again, you are given the network. And what you want to achieve now is, suppose that you're a salesperson. So you want to visit all these cities exactly once and come back to your, and you want to do it the shortest way possible. And observe that for the TSP again, there are exponentially many ways to do it. Okay. But turns out that in the worst case, you may have to visit, you may have to look at all routes. Okay, so this is not exactly the way it is, but I'm trying to make it. So that's why theoretically it is something called NPR. If you're interested, you can search for what NPR means and what is that question. CS people are crazy chance is P is equal to NP or not, which is roughly means that are there any real difficult problems to solve, or is it the incapability of human beings for now not being able to solve? Okay. I formulated that.
We will say, like, will we break all internet security one day or not?
Yeah, exactly. So there are different ways in terms of. For now, we don't know if we can solve the NPR problem efficiently from a theoretical point. But for empirical reasons, we see that you can solve really large problems, tens of thousands of nodes involved in the TSP problem very efficiently. So I know some optimization people who dedicate their lives to solve it.
Question, is that optimal guarantee or near optimal?
Okay, so that's a good point. So I will also mention it. Okay. Now, but I talk about optimization. But what is really optimization? So here's a quote from George Danzig. So George Danzig is pretty much known as the founder of the operations research field. So I can't tell you that, but maybe it will take me a few minutes. So maybe you have seen this movie, Good Will Hunting. There's this janitor who looks at the bar and, well, miraculously he solves the problem. So it's a very distorted way of what happened actually to Danzig. So Danzig was a PhD student at Berkeley in 1937, 38, something like that. And he was studying statistics, I think. And he was late to a lecture given by Jerzy Neyman. So Neyman is famous for his work in statistics. So if you have taken a graduate level course, you may remember Neyman Kirsten Denmark, for example. And Neyman wrote some questions on two particular questions. And Danzig was late to the lecture, so he sat down and rushed through writing the questions on this notebook. And then after the class, he looked at the question. Well, it seemed really tough to him. And then he tried so hard and eventually solved it. And then they turned it into Neyman, thinking that it was a homework. But actually, so Neyman just wrote two open questions in statistics. So unknowingly, Danzig actually solved two open questions in statistics with the PhDs. Okay. So it's something else. Okay. So this is how he describes the optimization or mathematical project. So if he lived today, maybe he would use different terms. But I think we can still understand. So if the system exhibits a structure which can be represented by a mathematical equivalent called a mathematical model. So mathematical model, we still use it today. Probably means different things to everyone. Okay? So biologists also use mathematical models, statisticians use, optimizers we also use. I just showed you one example. And if the objective can also be so quantified, so this is interesting because before Dantic, first people were trying to solve optimization looking problems, but they didn't have this idea of putting an objective function. So he is kind of the inventor of objective function, so which is very interesting. And some computational methods may be involved. So he's talking about an algorithm for choosing the best schedule of actions among alternatives. So as again, I told you for the NERSEC problem, our alternatives are the subsets. So he wants to find the methods to find the best schedule of actions. Essentially meaning that give me an optimal solution. Then if you can do all these things, that he calls them as mathematical programming. So there's a relation with computer programming, because he was thinking that, well, if you create an algorithm like this, you have to program it. So that's why it's related to programming. But it's not actually computer programming. Anyways, and if you look at a very generic optimization problem, it's something of this sort. So you want to minimize an objective function or maximize the function. And then you may have some inequality constraints, you may have some equality constraints, and you may have domain restrictions for this. So some of them may be real numbers, some of them may be integer numbers. Right, so this is very generic. And if you don't have any particular structure on functions or the domain or type of the functions, etc., then yeah, it's really hard to solve unless you have some special. Okay, but what do we mean by solving optimization? So sometimes the term optimization is used very liberally. So everyone thinks that they are optimizing things. For an optimizer, that's not how it works. So let me explain what I mean by this. So solving an optimization problem means that you need to give me a feasible solution, which is also optimal. So you have to prove me that it is. Okay, so that's very important. So for an engineer, for example, who wants to do some real stuff, right? So maybe the engineer might be happy with a feasible solution that is better than what people have achieved. Okay? So that's an achievement, right? So you do something better than other people's did. But optimizers are very picky people. Okay, so that's not enough. We want to see, understand whether this is the best you can achieve or not. So let me give you an example. So suppose that you have an optimization problem solving your thesis, maybe, and you know all the other people have found the value of 200 within and your thesis gives 100. Okay. From 200, you reduce that to 100. This seems like a big achievement, right? And you know, I'm a very picky optimizer, and I'm in the thesis committee, and I ask you, okay, why are you so happy? And you just find this solution 100, but you don't know if 0 exists. Right? Maybe you are still doing not very good compared to the real optimal. Okay. So without having a certificate or optimization guarantee, an optimizer is never happy. So really visible lights. It's optimization. Okay, but not quite. So there are ways you can find some optimality guarantee. Maybe you cannot prove me that 100 is the optimal solution, but you can prove me that no better solution than 99 exists. So that's still good, right? So that's kind of answers your question. So if you give me a feasible solution with value 100 and lower bound, right? Well, okay, the gap is 1%. I can be happy. Okay. Now at least I know that you did something. Right? Of course, the way you can achieve this lower bound is very tricky and depends on the problem structure. So that's where the science comes. Okay. And here is a sort of an illustration to hopefully convince you that this idea is valid. So suppose that you want to minimize this non-convex black function. As you can see, there's this global minimizer and a local minimizer here, which is a local maximizer. So it's a nested function. Same. And well, of course, this is just in 1D. You can do OC, you can do things. But suppose that you have hundreds of variables, and it's a really complicated function. You cannot really draw. So you need a systematic approach. But okay, so if you give me any point in the domain, it gives me an upper bound for the optimal value. Because maybe the optimal solution is better. So that's why it's done. Maybe. So maybe you give me this point. Well, its value is an upper bound for the actual unit. Good. So it's good to have. But as an optimizer, I want this lower bounds. So that's why this blue curve comes in. What is the nice structure of the blue function? It is convex, so it looks upwards everywhere. And what's nice about convex functions is that they are typically easy to minimize. So you can find their global minimums. You cannot always take the derivatives of sequences, so it's not that easy. But there are systematic ways you can find a circle of this function. But now you're in the game because this will give you lower bounds for the optimal value. It might be a little bit far, but this gives you a benchmark. And you have an upper bound, and then you can compare how to do that. Of course, the trick is how do you find this blue function? Right? So there are ways to do it. I will not explain this today. But you can even do more steps. You can subdivide the domain. You can get your blue function looks more similar to the black function in these subdomains. So you can divide and conquer. You can divide things like this. So this way, hopefully, you don't need to look at all possibilities. Okay. By just looking at small number of possibilities, you prove things like near optimal.
Can you explain a little bit of relaxation?
Okay, so relaxation means, let me go back. Relaxation is technically defined as a lower estimator of the function f and a superset of the region defined by the constraints. So you make your feasible region bigger, okay, and you underestimate your function.
You relax some of the restrictions.
Yeah, we relax the restrictions so that maybe the feasible region is bigger. Maybe you include some infeasible points. Yeah. But that's fine. So because it's a relaxation. Okay. So okay. Okay. So I told you that we as optimizers use the vibes, but not always. So there are cases in which we are happy. So for example, linear programming, the one invented pretty much by density, the solution method for the syntax. So in linear programming, all these functions are linear. Okay, so you are allowed to add decision variables and you are allowed to multiply decision variables with constants. So that's it. And there are no integer variables. So it turns out that these problems are easy to solve in the complexity sense. Not necessarily using density, but using some of it. And as an optimizer, if I can formulate a problem using linear programming, I will be really happy. Because there are really good solvers like really which can solve these problems. Okay, what if you cannot formulate the problem using continuous variables? You need to use this integer variables, like the next problem. You cannot put half of the item. Right? So you either need to select it or second. Okay, so typically, although these problems are hard in general, I'm usually happy if I end up with an integer linear program because I got this Groby, Simplex, Express, all kinds of advanced solvers which can help. Right, but maybe your problem is nonlinear. So then, if depending on the nonlinearity, you can still be happy. For example, if you have convex programming problem with no integer variables, I'm usually happy in this case too, because there are good solvers for this task. Well, you can also throw in some integer variables on top of nonlinearity, which is convex. I think I can solve some of it. Depends on many things, but I'm hopeful that I can solve. All the other problems which involve non-convexity, for example, okay, they are much harder. There are still solvers for that task, but they are not as developed as the ones that you can solve this class. I work on non-convex optimization too, in addition to problems of this sort. Well, these problems are easier to solve. But why do you think I explain all these things to you? What's the relevance to the topic of today? Well, these MILP solvers, these linear solvers, they've been developing for the last 30, 32 years. I think the first commercial one was really from 1991, when I was 3 years old. Right? So it developed a lot in the last 3 decades. And now they are 1 million times faster than they were 30 years. And this does not include hardware. I think that's really significant. And well, okay, there's a better implementation aspect. Of course, we can implement things better. So that's more from CS side. But most of the improvement is due to the theoretical advances in understanding the problem structure of essentially. So this is an example in which doing science, doing things on the using paper and pen and proving things, etc., actually paid off in terms of the technologies. So sometimes I give this example. If you have this machine from 1991 and you started running an optimization problem that day, it would still be running today, assuming that it has enough memory. But now maybe you have just solved that problem in a second. That's trivial. What is important to us is that I'll talk about this later on. The static deterministic version, that means of the biological time machine problem, can be formulated as a mixed engineering problem. So that's why we can take advantage of all these improvements we have done to solve our article. I think that's really nice. So any questions about this very brief introduction to the optimization process?
Where does the name time machine come from? Like programming biological time machine?
So some people use that terminology, the concept of time machine, and we are just using that. I will give you the precise reference who uses it.
You said that this solver started at 91.
Yeah. So the first solver was, the commercial one was developed by iLog, a company called iLog. Then IBM bought that company, and they called the solver C-Plex. So it's still operational today. But then the people from C-Plex actually left to form Robi, which seems to be much better than C-Plex. Yeah, so that happened like maybe 10 years ago or so. So Robi, because they hired the best people from C-Plex, they were able to do much better things than C-Plex does. Okay, but I need to give you one more example from operations research. An example of a stochastic, really simple stochastic process called the Markov chain. So here's the example. Suppose that you live in this strange city where weather is either sunny or Istanbul although Istanbul is a strange city, it's not following this. Right? So today it's cloudy. Okay, so it's sunny or rainy. And it's strange in the sense that we can forecast the weather tomorrow based on the weather today. And you don't care about it. Okay? Let's assume that this is our assumption. So you may question this. Well, okay. Can these kind of problems or situations really exist? Yes, they do. I'm just overseeing. And okay, so what we did is, you live in this for long, and you computed these probabilities. So these are conditional probabilities. Maybe I should explain what conditional probability means. So we want to understand the probability of tomorrow being sunny, given that today is sunny. Okay, so it's conditioned on the fact that today is sunny. And these numbers are given to you. And maybe you want to understand a question of the following. So today is November 7th, right? And suppose that today is sunny in this strange city. And you want to understand the probability that 2 days from now it is raining. Without knowing Markov chains or anything, I think you can sort of get a crack in this. So how do you think you can solve this? With right things.
Branch it out.
Exactly. So in probability, the thing is, if you don't know where to start, you start counting. Okay. You enumerate and then get the heads. So I could have done this case Can suggested. So today is sunny. Tomorrow is either sunny or rainy. And 2 days from now, it will be sunny because tomorrow was not sunny, and then you branch. It could have been raining, and then you branch, etc. So you can do this by counting. But how about, and this will be relevant to us. I will show you why. But how about this next question? So what is the long-term probability of learning a rain? Now that's not so obvious. That's not so obvious. Okay? So you can still answer questions on this, which will not be that relevant to us. But I thought that this is interesting. So that's why. Here are the answers. If I ask this question in our operation 3 course, Samanchi University, we discuss topics like this. So you define this Markov chain in 2 states. It's either sunny or rainy. And then you form so-called transition probability matrix. So here's how you understand it. So the rows represent today and colors represent tomorrow. So given that today is sunny, tomorrow will be sunny with this probability, tomorrow will be rainy, given that today is sunny with this probability. So that's the way you understand it. I think some Russian people do the opposite. So that's very confusing.
So what is today is the column for the row?
Rows are today.
Okay, and column tomorrow.
Yeah, exactly.
So you pre-multiply.
Yes. Okay. So if you want to post-multiply, you have to. So that's the Russian. So they want to do it together. And for every Markov chain, you can also represent it by this type, which is probably more intuitive. So if it is sunny today, it's 80% probability to remain sunny, or it will switch to rainy with 20%. Now, I can answer the first question like this. So given that today was sunny, what's the probability that from 2 days from now it will be rainy? That is exactly 2-step probability. And how do you get to 2-step probability? You multiply the matrix with this. So that's the way you get to the 2-step probability. So that's a really nice property of probable transition probability matrices. Then suppose that you multiply this matrix with itself. You form another 2 by 2 matrix, and then you look at the SR entry, and I did this, turns out to be 30%. And the important thing is that I don't care what the weather was yesterday in the market. So no matter what you did in the past, it's all forgiven, and you start the process. And to answer the second question, what's the long-term probability of observing a rainy day? So that's essentially what you multiply this matrix with itself infinitely times, and you observe that it's actually converges to something which is uniform in groups. Okay, so that's an interesting property. By the way, this structure doesn't happen for all market chains. Okay? So it has to be ergodic or periodic, whatever, so that is the conditions. You don't need to worry about it. But yeah, if you are lucky, you can multiply it infinitely times, and you don't need to multiply infinitely times. There are the ways by solving a linear system. Yeah, all these things are we teach in the undergrad stochastic modelers. Well, if this was too simplistic, I can give you one more example. Now, suppose that there's this other scheme where the weather tomorrow can be forecasted, but not only using today, but also using yesterday. Okay? So you observe yesterday and today and predict tomorrow. So here is the question. Can this be a Markov chain? The way I described it. It's a trick question. The answer is yeah, but you have to define your states carefully. Now, instead of defining 2 states, now you have to also consider yesterday and today as a pair. And if you define your state as a pair, then it can be a Markov chain. Okay? What I mean by this, for example, there will be a state of time sunny, sunny, which means that yesterday was sunny and today was today's. And sunny, rainy means yesterday was sunny, but today is rainy. Now, somehow you put the past in the state description. And based on this, you can now predict the state today, comma tomorrow. Of course, there should be some consistency. And here is what I mean by this. For example, we cannot switch from sunny, sunny to rainy, rainy, because the second index here should match the first index. Yeah, so you can do more complicated things. So that's just my. Okay, so this whole process is called discrete time Markov chain. And if you have heard of these terms, Markovian or numerist, this is exactly what it means. So what happens before coming to today is irrelevant. So you just look forward. Okay. And it's called discrete time because you review the process at discrete time, which are deterministic. So there are other versions of this as well. Continuous time Markov chains, etc. So in which you don't review, you review continuously. And this, I think you have this observation. If you look at the transition probability matrices, all entries are non-negative and row sums are. So that seems very obvious, but it has some implications for us. And then using Markov chains, you can try to answer different kinds of questions. Okay. For example, the first one I already talked about, the probability of being in a certain state after a specified number of statisticians, the long-term probability of being in a state, or the probability of being observed in a certain state. Of course, you cannot answer question 2 and 3 at the same time. So that, because a macro chain doesn't allow this to happen.
What do you mean by observed?
Okay, so what do I mean by observed? So think about you are a gambler, you go to the casino. So you will only leave the casino money, or you get all the casinos. Then there are two observable states. Either you are poor now or you are extremely rich. So these two states are. So that's called gambler's win. Again, operations research people came up with these weird things.
So you're asking what is the probability that you lose on your money?
Yeah,
so
exactly.
You lose the number of steps answering this question. Is that what you meant when you said number to answer you cannot solve?
Yeah, because yes, exactly. Because in the second question, the assumption is that the process will repeat itself.
It's conversion.
Yes, so-called state distribution. And the gambler's win is not exactly the case. We cannot repeat the process in times. You're either broke or with the generals.
Thank you.
But it's not like the last, it's a particular case of the second. Like, eventually, it is absorbed in the long-term state is 1 for that and 0.
Okay, so you can interpret it like that. So yeah, so I didn't make it very technical. Yes, but you can. Yeah. And what I care about, I don't care about chains and there's matrices. Well, I think this is the first time antibiotic term comes in. So you can model the effect of an antibiotic as a discrete time. So this is what people did. And we are using their model. So I think this is a very good point to ask questions, because I will move forward with the time machine. Any conceptual questions? I think I spent too much time on this.
If instead of, for example, looking at 2 days, we 10 days, 20 days, does the complexity increases exponentially?
Yeah, it does, because now state description has this 10 character string, and it can be 2 to the power 10 many states.
So does it become NP hard to solve?
Okay, so for macro chains, there is, well, the concept of NPRs is relevant for optimization problems. And maybe you may want to formulate these as decision problems, and then think about the complexity. So that's a possibility. And you are right, if you have exploration many states, then this kind of answering these kind of problems could involve more computation. So yeah. Okay, so time machines. What's the relevance? Okay, so I think these are slides which you should know better than me. So antibiotic resistance is an alarming global healthcare issue. And so-called antibiotic time machine problem is a way to understand this issue and propose a way to reverse it. And the idea is a little bit strange actually. So why do we have this resistance issue? Because some antibiotics are overused, right? And bacteria became resistant to them, etc. And the idea is to use the non-antibiotics in a different way, potentially, and so that you can go back in time and reverse this antibiotic resistance issue. These are some references, and these people have looked at this problem from the side.
So just, biological update. So Andrew Berry comes to Sabancı University every year to do evolution seminars, and several years ago he showed us a paper about malaria in Asia. some of the drugs that they couldn't use anymore because of resistance, 20 years later, they saw that it's working. Because, you know, when you stop using them, somehow the bacteria evolved back to a state where the drugs would work again, and somebody noticed that. And so if they knew about this, they could have actually planned them, maybe have had a shorter span. If, you know, so you think it's a huge problem, but actually it's something that also observed in the real life.
Yeah, exactly. So here is more mathematical description of the problem. So suppose that I have these genotypes or states in the microchain window, and I will denote this by a string of size A. A because I have A many alleles or genes. I'm never sure about that rights if I turn to it here. But this string has characters, A characters, right? And each character can be either 1, meaning that allele is mutated, and 0 if unmutated. Now, as you can see, if I give you an A, then there are 2 to the power A many steps, because you need to look at the string with all these possible characters. But one particular genotype is very useful for us. It's the one called wild type with all unmutated alleles. So that's where we want to go back. Okay, so here is the relevance to the microchips. So if you give me an antibiotic, and if I apply that to the genotype spectrum, then the state to a different genotype is governed by a probability, which I will denote by nk. So this k represents the antibiotic. So potentially I will have new. Okay. So I will give you an example. And well, for the first talk, let's assume that these matrices are given. They're served. Okay. There's no stochasticity in the entry zone. And the aim in the problem is to maximize the probability of state to the wild type in n steps using a sequence of these types. So the parameters here are these matrices are given to you, and we specify how many times to apply this antibiotic. So you don't need to apply the same antibiotic all the time. So we can switch between antibiotics.
So the superindex K means is identifying a matrix for every
antibiotic. Yes. K is the index for antibiotics. And for now, let's assume that we determine this sequence in the very beginning, and you don't observe what's happening later. So that's the assumption for this section. Okay, here's a picture. So here we have 8 genotypes or 8 states, and they are represented by these triples of zeros and ones, and you see 2 microchips, the blue microchip and the red microchip. And if you look at it very carefully, you will observe that using only the blue microchip, you cannot go from 111 to 00. There is no way you can. Okay. I think that's clear because from 000 there is no entry blue arc. But for the red microchip again, you cannot go to 000. Okay. So that's why I created. But if you use them in a collaborative fashion, so to speak, you can. And here is one example. If you do blue, blue, red, then with some probability, some positive probability, you can go to 0. And why? For example, if you apply blue, with some probability, you will get to here. And if you apply blue again, with some probability, you will go to 0, 0. And finally, if you apply red, you will go to 0, 0, 0. It's something. Maybe not with probability 1, but with something. And the antibiotic combination problem asks you to find me the best sequence of applications without observing what's happening. Okay, so here is the more mathematical explanation of the problem. So suppose that we are given these vectors P and Q. P represents the initial distribution, essentially where you start, and Q is the desired distribution, which means that you want to end up at the y-flag. So it's the unit vector where you put all the weights to the y-flag and zero weight on the others. So I will give you a numerical example in a few minutes. And then you have this Markov chain matrices on case. And then we want to solve this optimization. What is this? So let me go through this. First of all, the decision variables here are the matrices Tns. And they should be selected from this collection. So for the first transition, let's say n is equal to 1, I can pick any of these matrices. So I have k options to choose by T1. For T2, again, I have the same options. So as we can see, we have exponentially many options. And what is the objective function? Well, the objective function starts with the initial distribution P. So that's why we pre-multiply. We pre-multiply the transition matrices, which are unknown variables. And then we post-multiply with where we want to end up. So this might be confusing. I have a picture. Okay. And the thing is that this seems really hard to solve. Reasons. You multiply variables. So this is nonlinearity. So yeah, nonlinearity most likely brings something. And you have this combinatorial choice of matrices. Okay, because for the first one, you can select k of them, for the second location, another k. So k to the power n many. And I will call this version as deterministic. You will see why in the second lecture, because the matrices are given to me, certainly. And it's static because I decide everything and I don't observe it. Okay, so the literature. Why do we call this as dimension? Here is the reason. So these two people are, I think, they do math biology research. So they actually prove that this problem is in p-height. And these guys are the first ones who call this problem is antibiotic time machine. They call it time machine because in their head they want to go back to the past and have all these genotypes unmutated. Okay. But I think it's a nice thing. So some people from optimization looked at this problem, not this very particular version, but mathematically similar problem, let's say. And I think the first attempt to solve it was from Mira and her co-authors from 2015. I will talk about it later on. So they did complete enumeration. So remember, there are k to the power n ways you can organize the solution, right? And they go through all of them. Now, recently, we started working on this problem, and I have an extension needed for information that I will quickly show you. Okay. So let's look at an example. So here I have two articles. And the question is, start from 1 and go to 0, 0, 0, 0, 0 with the highest probability. So how do we achieve this? Yeah, to give you a perspective, there are only 4 possibilities. I can do 1, 1, 1, 2, 2, 1, and 2. So I have four possible choices. which one is open.
I guess we can start with the two, which most probably takes us to 1-0. Okay. And then I guess if you're at that state, applying antibiotic 1
It's a good idea. Yeah, the thing is, we don't observe what happened in the position. But turns out that this is one of the options. So 1 is an optimal solution, or 1 is an optimal solution. Why? Because if I apply 2 in the beginning, that means probably 2 over 3, I will get 1-0. And if I apply 1 then, I will have 1 times 2 over 3, which is 2 over 3. Or if you do the 1-2 combination, again, you get to the same. However, if I apply antibiotic 1 twice, then with 2 over 3 probability, I will be stuck. I will be absorbed by 0. With only 1 over 3 probability, I will be 0, and the same thing. Of course, we don't want to integrate rates, but this is an example where we can solve this problem very easily. Okay, and formally, I define problem as follows. Given K antibiotics with their transition probability matches K, length of the treatment plan K N, initial state, and where you want to end up, final state Q. Determine a sequence of antibiotics to apply so that the probability is maximized. So here the sequence, the term sequence is important, because I decide everything that you do. Right, now you may be wondering how we obtain these matrices. Okay, where does it come from? Okay, so here's some biology involved eventually. So to get to the probabilities, what these people do, here are cultures, they actually measure the growth rates of genotypes under each. They go to their lab, they have this hundreds of tubes, I guess. They put the genotypes in the tubes, they apply the antibiotics, and they measure the growth rates. Okay. And I will denote this growth rate by omega. And then what they did is they used this assumption, which says that if I apply an antibiotic, I can either get 1 more mutation or I will lose 1 more mutation. And we will denote the possible transitions with neighbors with the mutation gene. And okay, here is the biology that I sort of understand. So suppose that I'm a genotype and there's my neighbor. If my neighbor is fitter than me, meaning that its growth rate is bigger than me, I want to become like that. Okay? So the probability of me being that genotype is positive. That's a reasonable assumption, I guess. I never know. But suppose that I have multiple neighbors who have all higher growth rate than me, then I look at their growth rates and create a formula about the probabilities of becoming like. But if I'm this neighbor and all my neighbors now elite me, then why would I become like? So if my growth rate is bigger than all my neighbors, I'm in abnormal state. But the exact probability is computed in 2 different ways. So the first one is called the correlated probability, in which the difference between me and my neighbor is a factor. Okay. However, in the equal probability, the difference is not a factor. It's just the neighbor being bigger than me is, I don't compare the size of my growth rates and its growth rates in an absolute sense. Okay, I just look at whether it is bigger than me or not. So that's why it's called equal probability. So I will give you an example. Yes. So maybe you have noticed these numbers in parentheses. What are they? So that they represent the growth rates. Okay. Now let's look at 1, 1. So its growth rate is 1 under the assumption. Its neighbors have growth rate 2 and 3. Now the difference between these two guys is 1, 2 minus 1. And these two guys is 3 minus 1, 2. So that's why I have 1 and 2. So I sum them up, put it in the denominator, and these are my probabilities. So that's called the correlated. In the equal probability model, they will just be 1 over 2.
Okay. Sorry, can you say it again?
Yeah, okay.
So you have the growth rate, you get the transition from the growth rate.
Yes, so I will, by looking at the difference between, so it's 2 minus 1.
Okay.
1 difference. So this is 3 minus 1, 2 difference. So
you normalize.
Then I know. In the correlated model. In the equal probability model, they are all the same. Conversion.
You will be half them.
Yeah. Okay, so this is just a reminder. And yes, here is the optimization problem, which seems like mystical, right? It's, what's that to be here? So here's how it works. Okay. So first of all, you create these matrices for each diagram. I think this is quite easy to do. Okay. I create these matrices, and then I want to solve this particular problem for this example. I want to optimize for 2 steps, so that's why I have T1 and T2. I initialize with the probability distribution P, but what is the probability distribution? Since I know that I start with 1, I put all the weight here, and the rest is. And since I know that I want to finish at 0, 0, I put all the weight to 0, 0, and the rest is. Okay. And then you multiply P transpose with first transition times the second transition times the final distribution. Any questions here? Again, let me quickly repeat. So you know where you start from here, and you know where you want to end. In between, you are allowed to do 2 transitions, which are denoted by T1 and T2. And T1 and T2 are either this matrix or this matrix. So this is how it works. Question.
So I can use these 2 matrices as a mix for each state. I can use first one and then the first one again and second one.
Yes, exactly. So that's why there are 4 choices here. 1, 1, 1, 2, 2, 1, and 2. Okay. Well, but how do you solve this problem using this linear program? Well, this is where it gets a little bit. So I will need to introduce some mathematical notation and integration lingo. So I will define these 2 sets of decision variables, X and K, representing which antibiotic you apply in each step. Okay. And then I also have this vector variable, UN, which denotes the probability distribution. But how do we use them? Well, first of all, there's an obvious constraint. So for each step, you can apply one of them. Okay. So that's why I sum over K and say, since X are binary, only one of them is correct, and it will be 1, and all the others will be 0. And this is I guess this is the most important relationship. So the distribution after the n step is precisely the distribution after n-1 steps times the matrix you apply in the n step. Okay, so let me. So the distribution after n steps is equal to the distribution in the previous step times the matrix that you apply in the n step. Now the difficulty here is that you don't know which matrix you apply. That's the decision. So that's why I'm multiplying that with x and k. Now let's think what happens if x and k is 1. If x and k is 1, this means that I multiply the previous distribution with the kth matrix. Okay? And for all the other x's which are 0, they are taken out of this summation because they are 0.
So the summation, in fact, is not a summation. It's just
one
of them.
You're
choosing
exactly.
one of them.
Exactly. I can write this in a different. But summation helps me to do optimization. Okay? Because again, this is a bit technical. I think you need to take probably 2 graduate level courses in optimization to really appreciate this. Okay. So what we do is essentially you think of multiplying u and x and define a copy variable. And here is the full formulation. So what happens is that, so let me go through this. So you want to maximize the probability of being in the wild type. So you start with the initial distribution, you want to be 0. Then you have this copy variables. So the copy variables sum to the original variable. But because of this, all the copies are just 0, since x is 0. So here E is the vector of 1. So you are summing up the V elements in the V. And if they sum to 0 and V's are non-negative, then the only possibility is that all the V's are 0, all the elements in the V are 0. Yeah.
What are the V's? Are kind of
V's are the copies of U's. So I have k copies of U's, and I call them. So the idea is that out of the k copies, k minus 1 of them will become a 0 vector, and only 1 will survive. And that will be the exact copy of U.
But they are up to UN.
Yes, there are some, yeah, they add up to UN. But because of this disjunction tree constraint, okay, k minus 1 of them is actually 0, because for k minus 1 of them, this x value scalar is,
and the E is
the vector of ones. So you sum up you sum up non-negative numbers and they sum to 0. So the only way this can happen is that all these elements are 0. Okay? It's really tricky. It's really tricky. But the one which survives, that the one you use in the end step, these V's sum to exactly 1. So that's why it's a distribution. And this is the correct distribution because they sum to the events. Yeah, it's very tricky. I know that it's and
so you have the V's are either equal to U or 0.
Exactly. Okay. So that's called the disjunction. I really saw that.
Okay.
And the probability distribution is governed by this equation. Again, all the V's are 0 except for 1. And that is multiplied by correct matrix. Now this is constant, and this is equal to even. Yeah, so there is also a theoretical background about why doing this is the right thing to do, but I will not. Let's see some numbers and then so we use this data set from reporters. So they actually looked at 15 antibiotics and they measured the growth rates, 16 genotypes, and Yeah, so that's great. And I use my personal computer to do the experiments. And well, the solver we use at time. And these are the numbers. So let's try to understand what's. Well, first of all, the very first column is the initial genotype that you start from. And we always want to go to the 0, 0, 0. And the numbers reported here are the probabilities of reaching the 1. And we have a column which represents the treatment length. And I have this border. So I draw this because Mira and her co-authors did until n=6 using enumeration. Okay. And you see the enumeration time on my machine is this much. And I repeated this using my NLP. It takes this much. And they were not able to, maybe they didn't want to report it for greater than 6, but I estimated how much time it would take on my machine. And here is the actual time it took on my machine to solve this. All right, and I think what's important is these red numbers. So red numbers are bigger than Mira and co-authors numbers. Okay? So that's why if they could have solved bigger problems, they could have obtained better results, which they couldn't do because of this computation barrier. So yeah, in the paper I reported everything up to 15 transitions. So for the EPM model, there's a significant difference sometimes compared to ND56. Something I don't understand really. For the CPM, there's not much difference. Okay, so with n is equal to 6, they get to the good numbers, which they didn't know were good. But now I run this algorithm until 15 steps and pretty much always get the same. In fact, this same number is 0.617. Maybe, yeah, maybe there's a theorem.
So the CPM is where you take them equal.
CPM is where I look at the difference, and difference factor is correlated. EPM, they are equal.
Okay, so actually this is CPM is the one that you probably prefer to use.
Yeah, potentially. It probably makes more sense.
It's more realistic.
Yeah.
So it converges faster.
Well, in the second lecture, I will also see the observations.
Testing the lab. This is something that you can go to the lab and test, no?
No, not me, but somebody.
Yeah, you, yeah, we.
Yeah. Maybe not also you, but.
I mean, people who do biology with this, not with this. So yeah, there will be like the structure of the matrix kind of condition what is the best thing you can get, and you convert it faster. So,
yeah, so there's something to do with structure of the
kind of the maximal flow that you can get.
Okay, I don't know how much I did in terms of the time, but
it's perfect time. We are just watching.
Okay. So here what I want to do is to explain why I call the previous lecture a static deterministic version of the problem. Then we will look at different versions of the function. And here is what I want to do. So I will very quickly remind you that it's the version, but the rest will be new material. I'll talk about the dynamic programming formulation for the dynamic deterministic. So here I will call this the dynamic version because I will assume that once I apply an antibiotic, I will observe what happens and make my decision based on the evaluation. And then, but the most important part in this presentation is the idea of stochasticity. And this will come from the stochasticity in the antibiotic matrices. And the very reason is as follows. So probably you know better than me. So if you do an experiment, you want to repeat, see the variation, right? And in this context, if you repeat the growth rate experiments, then you may get a different vector. And then the question is, okay, which growth rate I should use to create my matrices? Okay. And I will formulate a problem in which we will consider all these different replications of the experiments, growth rate experiments, and create a solution algorithm. So I will explain the details. And then, well, if you have the dynamic version and the stochastic version, we can also have the dynamic. Okay, so here static means the following. I decide what to do at the very beginning without observing anything. Sure.
Which is what you did previously.
Yes. Yes, that's the term. Dynamic version means that I apply the first antibiotic, I observe what happens, it's my next state, and then based on that observation, I design the second step.
Which means you will update the probabilities.
I will decide the second antibiotic after observing the first transition.
Okay, it's in your, weather example, if we're asking what's going to happen today's rainy 19th, you will know what 18th is basically.
Exactly.
Okay.
Exactly. So I will observe the uncertainty, so that's so this is the difference between static and dynamic. Now, the difference between deterministic and stochastic is as follows. So in the deterministic version, you do this experiment in that only once, and you record the growth. And based on that, I transform the vectors to the matrix, and that's all. And then I solve it. Now, this Mira and her co-authors have a follow-up paper in which they replicate the growth rate experiments. Now they have 12 replications of the same experiments. And then the question becomes, what do you do with this all data sets? Okay? And they didn't know what to do, I think, because they didn't use this enumeration idea to solve the stochastic version. So they just reported this, and they have this box plots about the variability, and that's it. That's their way. And what we want to do is, considering all the uncertainty in growth rates, how do you devise a solution? So that's what I would call as the stochastic.
Okay, so uncertainties in these kinetic measurements is actually because on the log scale they make sense.
Mm-hmm.
Like 2 and 4 is more or less the same number for them.
Okay.
Right? I mean 2 and 20, so that's so every time they measure, they have these error bars.
Okay, so maybe that's very important.
In my opinion.
Okay. Glad to hear that, actually. Okay. I will explain this when I get there, but somehow we will need some kind of sampling procedure at some point in time, and I will explain why do we need it, how we do it when we get it. Okay, so let me remind you the deterministic model so that you can compare it with stochastic model later on, but also static versus dynamic. So some slides will be repeated on purpose so that you can see them. Okay, your favorite example from today. Now, in addition to the static problem, I want to motivate the dynamic. So what was the issue with the static? Well, after you apply 1 1, well, you don't know whether you went to 1 0 or 0, and you blindly make your second. second step. Now, in the dynamic version, if I can actually observe what happens after the first transition, obviously I can do that. If I end up at 1, 0, then I would choose antibiotic 1. If I end up with 0, 1, I would choose antibiotic. And obviously that will give you the probability 1, duration 0. Very interesting. Because you have more information, there is a way you can make this. So this definition you may remember this slide. So again, the important part is that we decide the sequence of dynamics. Now in the dynamic version, we call it a policy. Policy means that your decision is a function of the number of steps you have taken so far, plus where you are at the moment. Okay. So that's why a policy you can think of it as a matrix. You have the rows as the number of steps you have taken so far, and the columns as where you are. Okay. So you have to look at this matrix to decide your action. Okay. And again, this is just a repetition. We have talked about this. I recall that we can formulate this as a mixed program. And again, remember the main idea. We had these X variables representing which decision you have taken in step n. I remember this recursion. The distribution after the n step depends on the previous distribution times the matrix we have right. And we have this complicated linearization idea. Now, it seems like for the dynamic version, well, why not try it out? It's a tool we learn, so. And maybe there's a way we can. Okay, let me translate the dynamic problem to a mixed linear problem. But observe one major difference. Since we are in the dynamic version now, the decision variable will have one more input. So the decision you make in the n step is antibiotic K under the assumption that your state is I. Okay, so we add one more input. Okay, so that's why this logical constraint is now different. Because I have to choose an antibiotic K for each n and I need to know how many steps I've taken so far, and I need to know where I am to make my next. Now, the recursion is different. And the very reason is that we can no longer multiply the previous distribution into matrix. Because there is no matrix. I just have the rows. So depending on where I am, I should choose the correct row. Because my decision about the matrices was that, well, if you're in the third step, you choose this matrix. But now, if you're in the third step, and if you are in this particular genotype, choose this vector, which is coming from the matrix that you choose. Okay? So that's why this is an important difference, the recursions. And unfortunately, that complicated disjunction idea doesn't work. Well, it can work, but you may have exponentially disjunctions. That's not. But luckily, so there's a well-known technique in optimization to linearize the product of continuous variable U. Remember, U's are the probabilities, which can take any value, and a binary variable, X. So if you multiply a continuous variable, bounded continuous variable, times a binary variable, you get equivalently. So there's a known technique I don't want to. If you all do all these things, you end up with this complicated looking. Since I will not be using this formation much, I don't want to go into details. If you're interested, we can still discuss it afterwards. But my point is that we tried this, but this MLP doesn't scale the computation. So you can still use it, but you have to. But luckily, this problem has a very nice structure. So that's why, although you cannot see it, we can use the DP formation. So maybe it's a this will work for most of the slides. Okay. So how many of you are familiar with the term dynamic programming? So maybe more people have heard dynamic programming than people that know engineering. So dynamic programming works in situations where you typically have states and stages, and you make decisions based on your state and state. Okay. Typically. Here, the situation is as follows. Suppose that I know the initial state. I denote the initial state as my initial, and I know where I want to go, which is the final state. Okay. And then so this is a very important definition. Let's try to understand. So I define mu n of I as the maximum probability of reaching the wild type, given that I'm at state I after little n transitions. What does that mean? So I'm in state I after little n transitions. So I don't care what's it. I'm just here. And then I ask the question, with my remaining budget of steps to take, n minus n, if I do the very right thing, what's my probability of reaching the right? So that's the function. Let me give you an obvious value. Let me give you some obvious values. Now, if you have already taken capital N steps, then I know the value of this function for sure. Because either I'm lucky and I'm wild type, then the probability is 1. You're already there. Or you are not at the wild type, and then the probability of reaching wild type after n steps is 0, because you're already in a different state. You no longer have a budget to take another action, so you are stuck.
It's like the casino.
It's like the casino.
You win all the money or you got no.
Exactly. So you either win all the casino's money or you are, because you have no actions to take it. Does this make sense? Any questions?
Well, in all these problems, we have exact capital and transitions, right?
Yes. Yeah. So that's something. But we can sort of go around it. And I will allow, later on you will see, I will allow no actions to be taken as an action. Then you stay where you are. And that makes sense if you already reach wild type before capital. So it will be an identity matrix.
So the capital N can be very big.
Yeah. Well, given this value, for example, you can try to answer for the question, what is new capital N minus 1 of a state? right? Because now you have one decision to make, and you know what will happen after that decision. So this seems like you can go backwards and find all these values, because you know variable, you know the function at the last step. And to find the step before that, well, you can go backwards. And if you go backwards n many times, well, you end up with a value like this. Well, what does that mean according to our definition? Well, you are at I0, I1, I initial, and you have spent only zeros. What's the maximum probability of reaching the lifetime after capital N steps? Well, but that's exactly the problem I want to solve. I took no steps, and I know where I am initially, and I want to compute this.
You will kind of solve it backwards.
Exactly. So I will go backwards. And these are the alternatives. I think Bellman invented sort of programming. Just recently realized that he was also a chief in a biology journal. Yeah, I guess it makes sense. Okay, but what does that mean? Maybe I can explain you what's happening here. So suppose that you have taken little n steps and you are where can you go from? So if I take matrix and apply it, it will send me from I to j. And then the whole process will start over now with one more step taken, and I'm at j. And since the transition is probabilistic, I sum over to j. So I'm here now. You give me an antibiotic, I can go there, there. And I will start the process one more time with one less step to take. And since the step is stochastic, I need to sum over the j's, the condition. Now, the nice thing is that if you go backwards, you precisely know n plus 1. So that's why I can solve this simple optimization problem by simply enumerating over. Any questions? So I know the boundary condition. I will do backwards and find all the other values.
So that is your time machine. You're going back in time.
Well, in a different context. So this is the backward thing. So as you can see, I'm not calling a commercial solver. It's something I can characterize. So the student did. And it works perfectly well because what's the complexity? You do this loop n times and this loop for d times, and solve this very simple optimization problem k times. So that's why the dynamic version is actually polynomial solvable in the dimension of your matrices, the number of matrices you have, and the number of steps you have. There's nothing exponential. So that's very good, and you can solve the dynamic problem. So maybe some of you may have heard of decision processes. So this is an example of some macro decision process, which has finite minus states, so the number of states doesn't change. So that's why you can solve it. Of course, in typically macro decision processes, the rewards are added up. In each stage, you obtain the reward. So here, the reward is only at the very end. So if you are in the right state, you get the full reward. If you are not, you get. Right, so that's all I want to say about this. Let's switch to the stochasticity. which is probably more interesting. And again, here is your favorite example. Now suppose that you you went back to your lab, you did the experiment, and because this is a fictitious example, all the growth rates turn out to be the same, except for the growth rates at 0, 0. So it was previously 3, now it's 3 plus epsilon, a little bit bigger than 3 for antibiotic 1, and for antibiotic 2, it's a little bit smaller than 3. This can happen. But now the effects to the macro chains are very dramatic. Although the growth rates change only a little bit, you add one more arc, which wasn't there. From probability 0, you jump to probability, and also. So that's why, if you solve the time machine problem with respect to these realizations, the answers are different. Could be different and are different. Okay. Why? Because this change is really good because independent of what you did in the first stage, it will bring you to 0, 0 for sure. Okay. Because there are probability 1 arcs. Okay. So it's definitely optimal to use 1 step. Well, if you get 1 for the static, you definitely get 1. But there are now more ways you can get. Previously, there were only 2 policies, which gives you the 100% efficiency. Now there are. But what's happening? How would you decide what to do? Depending on Markov chain, your decision is different. But in reality, you don't know which Markov chain will be observed. So nature will choose. So that's what we call them. Nature will choose the answer. And your task is to decide your actions before nature chooses. Any ideas? What can we do in this case?
So here you are saying that you will experiment again and you change the matrix a little bit. I mean, the growth rate a little bit and the matrix change a lot.
Yeah.
Not going to have replication here, then do the experiment again.
Yes. Yeah. So stochastic counts just because you have done the experiment. You thought that you are doing the right thing, but then it's complicated. It's probably you are doing the right thing, but then the decision process should also do the Now, here's an observation, which took us a while to come to this observation. So, rather like I will just tell it to you, you need to think about it. So, how do you solve a static problem? Well, I have 4 options, right? 1, 1, 1, 2, 2, 1, 2, 2. And then what's the proposed thing is, well, apply 1, 1, the sequence 1, 1, to the first realization and second realization. They will give you some values, 2 over 3 and 1. Yes. If you choose this sequence. Well, if you don't know which one you will see, I'll take the average, it's the expectation. From instance, rather take the expectation. And it gives you 5 over 6. And it turns out that if you repeat this simple calculation, evaluation procedure for all the other policies, like 1, 1, 1, 2, 2, 2, you cannot do better than 5%. Okay? So that's an observation. Okay. If you do the dynamic, these 2 policies give you the highest probability, for example. But the nice observation is that if I take these 2 observations of Markov chains and take their average. I will call this as an average Markov chain, and solve the problem as if you have only observed that, like a deterministic problem, you get the same results. Okay, so I have a picture. So observe that this Markov chain is definitely different for all of the realizations. Right? Because remember, this arc was not here in the first realization, and in the second realization it was here, but with probability 1. Okay. Now we take the average, this 1 over 2 comes. Of course, it also has an effect here. And then you do the same thing for the second one. I think this arc was. And these are the average of the market. And turns out that if you solve the problem with respect to these averages, you get the same hypothesis. But observe that I had 2 different ways to get to the same number. Okay, in the previous slides, I have enumerated all my options and then take the average among the realizations and choose the one which gives me the best. But here, I take the average of the Markov chains and solve the problem with respect to these averages only once and get the optimum. And these 2 procedures give me the same number. Okay. Which is very good news. Why? Well, I can just take the average of matrices or Markov chains and solve the problem once as if it was determined. And I know how to solve deterministic problems, I can solve this.
There's some assumption about the probability every epsilon.
Yeah, so there will be some assumptions. I will talk about this.
But essentially, like, if different labs make the same experiment and they get different matrices, you can take the average of them and you can proceed.
Yeah, so yeah, that's what it is. Of course, there is independence assumption. You know, I will show you a slide where we have taken. Yeah, but it's the main idea here. So we have this Weimar functions potentially for a single answer. We take the average of them, we treat that as a representative of the uncertainty and solve for it. That turns out to be the right. Okay, so here is the modeling assumptions. So these couple of slides will introduce our application again. Yes. So suppose that I repeat the experiments R times. Okay. For example, these guys actually did it. So for, again, 16 genotypes, this time they used 93 antibiotics, even more, and they repeated the experiment 12 times. Yeah, they were real patient people. And let's denote the growth rates of genotype J under antibiotic K in replication R as this notation. J. So this has 3 indices. And here is the main assumption. So we will assume that the J's growth rates of antibiotic K is a random variable which takes these values with equal properties. What does that mean? So you repeat the experiments 12 times. Right? And for first genotype, you look at these 12 numbers and choose one of them. Okay? For the second genotype, you look at the other 12 numbers again. You sample one of them randomly. And so that's how you create a growth rate. So how many possibilities we have? For each genotype, I have R new choices. Right? So R times R times that's R to power B. This is quite a big number to get R. And here is one antibiotic from the data sets. So this is the antibiotic that we use. And these are the growth rates. So each dot is an experiment they have, and you see the genotypes. So there's quite a bit of variability.
Okay. This is biology reflecting, but here you are putting the concentration of the antibiotic. I guess when you say antibiotic, it includes at which concentration?
Yes, so in their data set, sometimes they use different concentrations for the same. So I treat that as different.
Yeah.
So in the hands-on session, you will have a chance to do that. Okay, but okay, even more notation. So how do we precise this? Well, I have this index S, which is defined as the Cartesian product of numbers from 1 to R multiplied B times. And well, now suppose that I will sample a growth rate. How can I do it? Well, again, as I said before, randomly I will choose one of these real experiments, and the value from that experiment will be my growth rate for this particular genotype. For the second genotype, I will repeat the same procedure, etc. So this way, you can create these vectors indexed by the antibiotic and S, which is the sample. So I will call this as a sample vector for antibiotic. Okay? And I have explanation in this samples. Okay, the exact number is here, R to E, if you R observations. And well, if you give me this vector, I know how to transform that to a matrix. We have already discussed this before. So we can use either the CPM approach or the PPM approach to get to the matrix. So this will be a sampled matrix. And again, in the hands-on session, you will have a chance to sample these matrices, and you can observe how different or similar they are. Okay. Now that we have MKS, I can define the static stochastic version. So what does that mean? So in this problem, the input is still the antibiotics. But instead of having a single matrix, I have this exponential family of matrices for each antibiotic. And so I give you these matrices. And I give you the treatment plan as before. I give you the initial distribution. I give you where you want to end up with. And your task is to find the sequence that will maximize the expected product. Because I want to use this expected term here, because each sample might give you different values. Then you have to make a decision which will maximize the expected performance. Of course, this is not the only way we can measure. Okay, but this is the easiest. And you will see some consequences. So the dynamic version is very similar. The only difference is that now we seek for a pause. Any questions about these concepts? Is it clear why we need to make expectation? Because again, many samples, the same decision may lead to different values. So it only makes sense to take that. Okay. Now, here is a horrible, even for me, this is a horrible optimization. So you have to make decisions, but once you make a decision, once you select an antibiotic, all its family comes. Okay? You don't simply select a matrix. You select all its family. So that seems really complicated. But luckily, we were able to prove that there's a way you can fluently solve a stochastic problem with a deterministic. So that's the nice thing. And let me show, to explain this, let me define the average transition probability matrix. So I've already shown you an example. But this time you take the average over the whole index sets. So this is an average of R to the power B matrices, interior. Suppose that I computed them and denote that by M. And then the proposition we proved says that we can solve the stochastic problem as a deterministic problem if you use these M bars. Okay. It all boils down to computing numbers. But why? Why? Why do we do this? Well, the proof is that's simple. That's short. I can say simply, but it's that short. You don't need to understand everything, but let me give you the main idea. Suppose that I have this random variable whose expectation is 5. And I ask you the following question. What is the expectation of 2 times x plus 3? Now, since expectation is a linear operator, so that's what conditions like to call, right? So you can take 3 out of the expectation and 2 out of the expectation, and this is equal to 2 times the expectation of x plus 3, which is 2 times 5 plus 3, 30. Well, it seems much different than this, but that's pretty much the same. Yeah, so that's why if you give me the average matrices, it's as good as giving me the whole thing. Yeah, so that's very nice. Why is this possible? Because, let's go back. This is somehow multilinear in this. So you can still multiply random variables as long as they are independent. And you can still do the trick.
So, question. So, if you give me that figure with the actual experiment.
Okay, let's go back.
My first thing to do is Canan, they will just take the average values of these and calculate a matrix based on the average. And it would have got some answer. But what you're proposing, no, construct all possible matrices with all these possibilities and then take the average of the matrices. It's a different result.
Exactly.
Okay.
Exactly. So actually we try. Yeah, so well, it's not the first thing as an optimizer, okay. But as a biologist, I understand if biology people would prefer to do it. So we thought that it's a good benchmark. So I didn't include it here. But it turns out that doing the averages here in growth rates and making these deterministic plots, so to speak, and then using those matrices is very misleading. Because it seems like if you do it, you can go from everywhere to 100% frequency. But once you evaluate it in all of sample, actually you have 0 probabilities sometimes. So it's very misleading.
Probably those outliers are.
Yeah, that's one thing. That's one thing.
But apparently the matrix building process is highly nonlinear. You change it a epsilon, you get a different.
Yeah, that's all right.
Because the values are so close to each other, they were off the charts.
No, but even if they move a little, you can get to a different, it's very kind of chaotic.
Yeah. Because you're taking the difference between the two.
Exactly.
And they are so close.
If that operation was linear, going from vector to fantasy, that probably does the same. So that's the main idea of the proof. Expectation is linear. Okay, so that's sort of good news because I know how to solve the deterministic problem, and now I have a stochastic problem, which can be used to do it. But there's something I'm hiding. There's a catch. how many matrices you have to average. Yeah. So that's the big one.
Yeah.
So I can actually never do this. It's a huge number. Okay, so if your population is too big, what do you do? You take a sample. Take a sample. Take a sample of fixed size, large enough, and take the average of that and use that as an estimator. So that's the idea. Okay, so this is not my idea. It's the operations research optimization. There is a whole field of stochastic programming in which people do this every day. Even more notation, how to do it precisely. Well, you give me the set S, which is a subset of a polynomial set. You take the average and call this M hat. So I put hat because it's an estimate. And then what we do is you repeat this for each metric, for each antibiotic. And you collect this in this script M set, and you go ahead and solve the ML with those average matrices. Okay? But this is the same problem as if it is. And then you compute its objective function value, which is this matrix. Pre-multiply by the vector. Okay, so this is all that we can do. But the thing is that just because I call this as the opt doesn't mean that it is the optimal solution, right? It is the optimal solution for this particular selection. And you may worry that, well, maybe you over-optimize and it's only working for this sample. But if you give me another sample, it will perform terribly. So for that purpose, we generate a new sample and compute the objective function value of the same decisions, so the same decisions on this new sample. So this is our sample analysis. That's why I'm calling this as evaluation. So I optimize and then I evaluate in a different sample. So if these two things are similar to each other, okay, so that's a difference. If they are really different, well, they're in bad shape. And for taking the average of the vectors and then the matrix, these two things are completely different. How about the dynamic? So this was all for the static. So we can play the same game for the dynamic too. So a similar proposition, you can still do things. You can still do the DPI, you can still do the DPI with the average matrices to solve the dynamic. So there is one more catch. I think that's the last part. Now, what is the evaluation for this step? So you give me the average matrices, I multiply. But for the dynamic growth, it's not matrix multiplication. So, for example, I start here, you tell me, okay, you move according to this. I move according to here. Then at this point, I move according to another rule again, etc. So it's the whole process. So that's why you have to do a forward DP. Just to implement that, you need to do a forward. Remember, we did backward DP to find optimal decisions. And now we use it forwards, starting with the initial and ending up at the final to evaluate the curve, such as luckily this is even easier than so there's no transient faster. Okay. before going into the numbers, computation results,
Right, but I didn't know. Maybe you can actually, so in the last case, you go forward, not backward. Right? The dynamic is custom.
Yeah. The backward solves the problem. Forward just implements that solution. That's the way you can use it to evaluate. Now,
Could I ask, does it evaluate whether the solution that we found is a good one or whether the S double dot is similar to S prime?
you will see the results.
Okay.
So they will turn out to be similar, so that's why we are happy. But in principle, you can even evaluate a really bad solution. But that can still be done with forward. Because forward DP doesn't optimize, it just gives you the function. Okay, so here is the computation setting. I think I mentioned these people have carried out all these experiments, reported them. So sometimes they even have replications of replications. They are crazy, I guess. So sometimes even they have 12, 24 replications. You will see that. And we just used 10,000 out of this R2 power. Just 10,000. And then we use this computer for experiments. We use a different version of probabilities, more recent. And we solve the DP for the dynamic stochastic version. We use MILP for the static version. And this is, I think we briefly talked about this. It's possible that we end up at wild type before capital N. And why do we waste the remaining around? So that's why we also added an identity matrix as in no action, no intake action, so that you can stay there if you want. By the way, it's still possible to use identity matrix in the static problem, which is very interesting. So in the paper we have an example. It's online in bioarchive, right? You can check it. So we have nice figures. Even in the static problem, sometimes it makes sense to use identity matrix. Just a little bit complicated. And here are the numbers. So here is how you should understand the numbers. Again, the very first column gives you the initial genotype. So we have the number of steps here. I didn't want to report everything, so just close for different values. And here in the sub column, you have the optimizer value. Here you have the evaluator. So these two are computed using totally different matrices, but the same decision. And then, again, as an optimizer, I'm really happy to see this. First, why? Because you see all these numbers are very similar to each other. Of course, I'm rounding. There's some rounding business. But, well, I just saw this one, 65 versus 66, and 70 versus 71, but more or less for all the others, they are almost the same, up to this round. So that's really very good. It's very accurate. So taking 10,000 out of this crazy number was tricky. So sometimes I joke and say that it's not far away. Okay, but for a biologist, maybe the numbers itself are important. So the probability of reaching the wild type is more or less 70% for most of the genotypes here. For some of them, it's easier to reach the wild type. But for most of the others, it's like 70%. What is the computational cost of doing this? Well, it's written here in the average time spent. So it's the average time to create the stable, it increases, of course, with the problems. I would love to solve an x equals 100, but it seems we cannot do it with this.
Because of time cost.
Because of time cost. And the memory will blow up, even for that.
Way to parallelize. Like,
okay, so Grow is already parallelized. So,
yeah,
so
no, but that is one way. Like, basically, you can have different initial points in different machines.
Yeah, so that can be done, but it doesn't really solve the problem. Each of them takes some of that. Okay, so for this was for the CPM, by the way. For EPM, we have similar observations. It's just that the probabilities are lower by constraint. CPM have high probabilities, typically in the Markov chain, or more focused probabilities. Other than that, they're pretty much the same. Yes. These are all for static. Yeah. For dynamic, of course, you can do better information. And here are the results. Now, even with 8 steps, you see that we're doing really good. And with 11 steps up to this precision, you get pretty much 99.5%. And the very nice feature of DP is that the CPU time is just less than 10. You can just create this table of square. There's no process. And for the EPM, it requires you to do more iterations, essentially, more n capital N. You need to choose larger capital N's. But still, it is good. Okay. Now, question that is probably practical. So I will give you an example which is not directly related to this, but I think similar. So suppose that you are sick and you go here. Doctor prescribes you some medicines, right? Potentially different for each day. And the doctor says that, well, take medicines, 10 days. First day, this one, second day, this one. And after 10 days, come back to me and I will check. So that's the static approach. In the dynamic approach, where the doctor says, okay, take this medicine, come back to me tomorrow. He looks at me or she looks at me and prescribes another one. And I come back one day after, etc. So that seems like a lot of work, right? And that's not how it works, at least in this context. So, well, okay, the dynamic is good, but we have to, there's some cost of observing. So that we shouldn't ignore. And we also looked at problems which are easy. So maybe you don't go to the doctor every day, but every 3 days. So how much you lose from the performance? So we want to understand this kind of issues. And with my PhD student, Dennis, who joined us in this, we are looking at sort of different version of the problem in which the performance is not defined as taking the expectation, but a different way, where you include the risk aspect. So just because the average is 0.5 doesn't mean that you are doing 0.5 all the real. Sometimes it might be 0, and sometimes it might be 100%, and then you take the averages. So one way to get around it is to maximize the average of the worst features. What we are doing is we are averaging 100% of the conditions. But maybe we should do, let's say, maximize. And this is one way you can incorporate it. Not the only way. But then you may lose a little bit much from the expected performance, but you can get better performance for the worst realization.
Why is average, not median, for example?
Okay.
What I'm thinking is like you take the 25 percentile and you try to maximize that one.
Yeah. Okay. So the median it's probably difficult to optimize, but
yeah,
the average of the worst 3%, this can be done with implicit.
But you have to sort them in order to get the worst.
You don't need to sort. So there's a formula which gives you the worst 3% of the vector. And it's a linear formula. Yeah. So it's really nice. So I didn't include it here, but there's a way. And maybe I can finish with the slides. I don't know how much you can see this light blue color. But if you do the risk neutrality, which is taking the average, you get a performance of 56%. But look at this histogram. With, I think there are 1,000 samples here. With 23% of the time, you don't go to one time actually. So the worst performance is really bad. That's reflected here. The worst 10% probability is. But then you do something else instead, which I will not explain. Then, well, of course, there's a trade-off. You reduce the average performance from 56 to 52, but look what happened to the worst 10%. It rose from 0 to 10%. And this is reflected in these figures. Sort of shifted somehow to the right. But of course, you also kill the good realizations. There's the trade. Yeah. So that's what we are working now. So the difficult part about this is that taking this average matrix idea, because the risk measures we use are not linear functions. They are piecewise linear functions. You cannot take the average and continue your life with that. That's the difficulty. So that's why you end up with really large scale problems, which were now straight away. Maybe some idea. Yes. So I think that's where I want to stop. Theoretical lecture. Do you have any questions?
You show the times, but just I'm trying to see how this can translate from, let's say, academia to practice. Do you think it's something that eventually we can kind of give to the hospital so they can to have the final impact? The 18,000
seconds,
1800 seconds, not too much. Like,
and it should be specific for each person. I will give you a table, and you will look at this table, and based on the state of the patient, maybe.
But is it phenotype of the bacteria, no?
Yeah, but for the hospitals, and for the bacteria, again, I will do this once, and I will give you solution as a matrix or vector, and then you will test it. So the cost is just one time total. The rest is just lab experiments. I'm sure doing these experiments take much longer than 10 minutes.
Finally, genotype.
Any other questions? In your future groups. In my future groups.
Okay, I have some ideas about this.
Okay, so for the risk cover, I think the question is for the risk covers, is averaging matrices idea. So that's why you have to model each sample separately in the optimization model. So that's why all these variables have one index, which is the performance in the sample. So that's why the size is empty. Samples. That seems like a really one challenging problem.
Another problem that you might be interested in is we don't always need to go to the wild type.
Okay.
You may want to avoid some of those mutations because they are extremely resistant. If you go in that path, you end up in a very bad place. So, you know, instead of just, you might want to optimize the probability of ending up with several not so bad paths or dead end paths, something like that.
So that is possible. Our model allows that, because remember there was this Q vector, which is your target.
Yes.
If I change my target like that, it's possible.
You can have a stable final state that you are happy with.
So if you give me a target distribution, for example, the target distribution will have 0 probabilities for these really bad genotypes, then I can do it. I can maximize the probability of not ending up in those states.